Welcome to the McMaster University course, Computing Software 701, Logic and Discrete Mathematics. This is Bill Farmer. We're going to continue to discuss the topic of recursion and induction, and today we're going to talk about well-founded recursion and induction. Okay, so let's say we have a relation R, binary relation, on a set U. And suppose we have a subset of U, and then we can say a value y is an R minimal element of S if y happens to be in S, and for every member of U. If that member of U is in S, then it implies that that member is not related to Y. So in other words, if we put Y on this side, there's no member in S that we can put here. There's no member of S we can put here to make this relation true, this statement true. So it's like saying we have a smallest member, but R is not necessarily an order. It's just a relation. So we say R is well-founded if every non-empty subset of U has an R minimal element. So that's what well-founded means. And we will say that the structure UR is well-founded if R is well-founded. And we have several examples. The less than relation on the natural numbers is a well-founded relation. The lexicographical ordering on ordered pairs of natural numbers is a well-founded relation. What this means is that if I had 2 and 1, that would be less than lexicographically than, let's say, 3, 5. That's because 2 is less than 3, but also 2, 1 is less than lexicographically of 2, 2, since 2 and 2 are the same, but 1 is less than 2. This is the same kind of ordering that you see for words in a dictionary. And then we also have that if we take the natural numbers with the successor relation, that means M is related to N precisely if N is the successor of M. This is also a well-founded relation because if we take any set of natural numbers, there is going to be some natural number in this set, let's just call it M, that does not have a predecessor. In other words, that there will be no R minimal element. So in other words, that M will be an R minimal element for this set. Okay, so let's talk about another notion, which we've mentioned briefly before, Noetherian structure. So again, we're going to have a binary relation on U. And if we take a sequence of members of U, that is called a descending R sequence. If when we start with the first member, we can find something that's related to like this, and then with that member we can find something that's related to it like this, and so forth. So we have this descending R sequence, and we'll say that UR is Noetherian if every descending R sequence of members of U is finite. And then we get this nice proposition: this structure is well-founded if and only if it is Noetherian. So we can think of these two notions as being basically equivalent. If we have a relation that's well-founded, that relation will also be Noetherian. Okay, so now we're ready to talk about well-founded recursion and induction. Okay, so let's say we have a well-founded structure, UR. Now we can define a function that takes some inputs and produces some kind of output that's defined by well-founded recursion as follows. The function is defined in X by some big expression, and that expression can contain recursive calls to F like this. And we will assign every member of the input a complexity which is a member of U. And then we also have this requirement that the complexity of these arguments for the recursive calls are less than the complexity of what we started with. If you think about it a moment, this definition is exactly the same as our definition of ordinal recursion. Where's the difference? The difference is that instead of using a well order, we use a well-founded structure. That's the only difference. So here, the complexity would be a member of a well order, and here we would have the well order. Otherwise, it's the same idea. So well-founded recursion is really a generalization of ordinal recursion. Now, we get a induction principle, which is written right down here. This looks like exactly the ordinal induction principle. The difference is here, instead of using a well-founded relation in ordinal induction, we use a well-founded, a well order. So in well-founded induction, we're using a well-founded relation. In ordinal induction, we're using a well order. Those are the differences. Okay. Now, well-founded recursion and induction generalizes structural recursion and induction, and it generalizes ordinal recursion and induction. So, let's say structural recursion and induction is probably the most useful kind of recursion induction for people doing computing, but occasionally we can have complicated situations where ordinal recursion induction is useful. But the general concept, the concept that includes both of these, is well-founded recursion and induction. Now there's a nice useful proposition that says if U R is a strict total order, then UR is well-founded if and only if UR is a well order. So another way of saying that, strict well orders are well-founded relations, and vice versa. Okay, so let's look at a couple examples for the natural numbers. The first is the well-founded induction principle for n and less than. Less than is a well-founded relation. We get, this is our induction principle. Basically, I just took the induction principle that we had up here, and I replaced R with less than, and I replace our set U with the natural numbers. And if you think a moment, this is exactly the same as strong induction. So strong induction is well-founded induction for the natural numbers. I should say well-founded induction for the natural numbers, where the well-founded relation is less than. Now let's think about well-founded induction for the natural numbers with the successor relation. Remember, the successor relation is that m is going to be related to n if and only if n equals m plus 1. In other words, m is the successor of n. Here we get this induction principle. So this is a well-founded induction principle. And this is essentially the same as weak induction. So for the natural numbers we talked about, we had strong induction and weak induction. We can get both versions of these induction from the well-founded induction principle by taking different well-founded relations. So for strong, we use the normal less than relation, and for weak, we use the successor relation. Okay, Now, we talked about bin tree being we talked how bin tree is a set of elements defined by as an inductive set, but bin tree with R is well-founded, where R is defined as T1R, T2 means T1 is an immediate subtree of T2. What that means is, so we have these binary trees like this. So if this is T2, the whole tree is T2, then this tree could be T1, or this tree could be T1. Those are the immediate subtrees. So basically we say the immediate subtrees are related to the tree, it's the whole tree, by this R relation. Okay, so if we think of bin tree with this R, that is a well-founded structure. And we get this induction principle. It's just the well-founded induction principle. We're using a particular R here. And if you think a moment, we can prove pretty straightforwardly that these two things are equivalent. Structural induction for bin tree and well-founded induction for bin tree R, they're basically the same induction principle. So this shows how we can think of induction over bin trees as being well-founded induction. Okay, that completes the subject for today. Our next and final presentation for the topic of recursion and induction, which we'll do next time, will be on monotone functional recursion. Thank you very much.